Good morning, everyone. We're going to wrap up with a couple slides here on chapter 11 and then discuss some parts of chapter 12, just actually some very small parts out of chapter 12. And then we're going to probably get into some review today. I think we'll be able to get through the chapter 11 and 12 topics. So we were on the slide last time, and I was just making sure I was knowing what I was looking at. So we have CO2's phase diagram on the left. What a phase diagram is attempting to show is at what temperatures and pressures does a substance exist as the phases of solids versus gases versus liquids. And so if we just said randomly, if we said, well, at say 1 atmosphere is here, and so if you're at a low temperature, you're on the left side. If we're changing temperature, we're going from left to right. So if we're at 1 atm and we're changing the temperature, imagine you have CO2 would be a solid at low temperatures at 1 atmosphere, so under atmospheric pressure. And so then when you hit this temperature right here at 1 atm, this is about for dry ice, minus 78 degrees C, that's the temperature at which dry ice sublimes to the gas phase. That's why dry ice, if you have a solid chunk of dry ice, it can maintain a temperature inside of, say, a cooler at minus 78 degrees C. So this is why sometimes you might use dry ice to ship ice cream across the country. It's because it's going to keep that temperature well below the freezing point of water. And so then CO2 would transition directly from the solid phase to the gas phase. That means that at atmospheric pressure, the only phase change possible for CO2 would be sublimation. So if you go direct from the solid to the gas phase, that's a sublimation event. And so there is a key point for substances, that's the triple point. The triple point is where you have the coexistence of the three phases. To be honest, I think people make too much out of the triple point itself. Sometimes teachers really focus on, at the triple point, you could have the equilibrium at that point between all three phases, which is very interesting. But more interesting, I believe, is that if you go to a lower pressure than the triple point pressure, then the only phase change that can occur is sublimation. So this is why some substances at atmospheric pressure, like CO2, can only directly transition to the gas phase. So if you ever wondered why solid dry ice doesn't melt like most substances do into a liquid phase, and why does the liquid phase not spontaneously boil at some temperature like, say, water does? So water at 1 atm undergoes the normal kind of process of going from solid to liquid at 0 degrees and then to gas at 100 degrees. And so we know these points pretty well at standard atmospheric pressure. And so we were talking previously that if you reduce the pressure, so if you have a vacuum pump reducing the pressure, or if atmospheric pressure wasn't as high, what would happen to water is that it would still undergo a normal melting process as long as we were above the pressure of the triple point. So the triple point of water is right around 0 degrees C and really low in pressure. So it's at 0.006 atm, so really, really low in terms of pressure. And so as long as we're above this pressure still, so if we're at, say, 0.1 atm or 0.01 atm, we're still above the triple point pressure, so water can still melt to the liquid phase, and then the boiling point's reduced. So we've lowered the boiling point because we've lowered the surrounding pressure. We were talking about this with vapor pressure. Water will boil when its vapor pressure is equal to atmospheric pressure or whatever the surrounding pressure is in the water sample. So we reduce the pressure, we lower the boiling point, and if we increase the pressure, then we increase the boiling point. So if you can increase the pressure in a pressure cooker, you increase the boiling point of your substance water. And then if you happen to go well below this pressure of 0.006 atm, if we're down in this region here, then ice can go directly to the gas phase. And you can have ice sublime directly from solid to the gas phase. And so that diagram also can give you insights into what happens if you pressurize a substance. So if we take really most substances as a liquid, so let's say we're at a relatively high pressure, close to 0 degrees, or maybe even in this region here of like room temperature. So we're just somewhere in that liquid phase for CO2. And you can imagine taking like a piston with a lot of force and pressing down on the liquid. You can eventually press the liquid molecules so close together that the substance will solidify. This is true of just about every substance that we know of. If you take the liquid and have it at least cold enough and put enough pressure on it, you can solidify it at a temperature at which normally the substance would have been a liquid. Now, water is really strange, that if you take the solid, and let me do a little erasing here. If we take a solid and some of the parts here at a relatively close temperature to the melting point. So if we're like close to -1 or -2 degrees C, and we take that solid and we apply pressure, we can actually liquefy. You can liquefy a solid by adding pressure. The consequence of that is that liquid water has and can have a higher density than solid water, depending on the temperature and the pressure that you're at. We know this because ice floats on water, so we know that ice near the melting point of water has a lower density and hence floats on water. So this consequence here is that the liquid water density is greater than the density of ice. And so the idea that ice floats on water comes from this part of our phase diagram for water. Now this is a very unique property to water, and only a few other substances have this particular property where you can apply a pressure. But the idea would be, you're just thinking applying pressure is up and down on our axis here. So by applying pressure, you're going up the axis. If you reduce the pressure, you're going downward. So changing the pressure goes this direction, changing the temperature goes this direction. So you can understand what phase changes a substance can undergo if you have a phase diagram available, and then you can understand at what temperature and pressure a substance will exist as, also with the phase diagram. Now there's one other thing here that you might be looking at saying, well, we haven't talked about supercritical fluids. What a supercritical fluid is if we get above a certain point of temperature and pressure. So if we're above a certain temperature and pressure, if you imagine you have a gas, so imagine it's an ordinary gas at a relatively high temperature. So imagine we're over here in our phase diagram. So pretty hot for a substance and then relatively low in pressure. So if you're imagining such a gas, imagine then you take that gas and you start adding pressure. So maybe you have a piston and you're like adding to the pressure, keeping that temperature where it is. And so if you start adding to the pressure, and you start to either put more gas into the container or you're reducing the pressure with the piston, you get to a point where that gas, you know how the ideal gas law breaks down because we're pushing the particles close together. You get to a certain point where the substance doesn't really behave as a gas or a liquid anymore. It doesn't necessarily explode. It doesn't lead to a negative outcome per se. Like when we say supercritical fluid, this isn't anything all that fascinating other than a substance that behaves as both a gas and a liquid. So a supercritical fluid is just kind of like a gas-liquid kind of tandem. So it just behaves like a gas, also behaves like a liquid. So what you get with the supercritical fluid is you get kind of like solvent behavior, but you also get a substance that will expand to fill its container, kind of like a gas does. So it has properties like a liquid, also like a gas. There's interesting utilities. Let me show the last slide for chapter 11 is a table of supercritical values. If you look at some of these critical temperatures and pressures, for nitrogen, it's a low temperature, well below room temperature, and then at a not super high pressure. If you remember, we did an example of N2 where we were at like a couple hundred ATM. Remember the end of chapter 10, we had a problem that was calculating the ideal gas law versus that van der Waals equation pressure. That was a super duper high pressure where that nitrogen sample was actually not even a gas anymore. And we were still relatively reasonably calculating its pressure with the ideal gas law. And we were better predicting it with the van der Waals equation, if you recall. But a supercritical fluid, the nitrogen in that cylinder, a lot of gas cylinders that you have relatively high pressures of, it's really more like a supercritical fluid of that gas inside of the cylinder. And so as you make nitrogen, bigger, or you make the molecule bigger, CH4 has a larger size. If you go to CO2, even bigger. Notice that we're increasing the critical temperature, we're increasing the critical pressure. The supercritical points, like the temperature points and pressures, these are directly proportional to strengths of intermolecular forces. So the stronger the intermolecular forces, the higher the temperature and pressure the substance will exist as a gas or as a liquid before it reaches the supercritical phase. Supercritical CO2 is kind of interesting in that this has a lot of industrial applications. So any chemical engineers in the room? Sometimes there are, I guess there's not now. But there's a lot of uses of CO2 as like a solvent. You can use supercritical CO2. It's actually one of the main methods that's used to remove caffeine from coffee to make decaffeinated coffee. Now, unfortunately, it removes other things than just the caffeine. That's why decaffeinated coffee generally tastes pretty bad. or worse than normal coffee or tea as well. But supercritical CO2 can be used as a solvent, kind of like an organic solvent, but it's industrially, it's an interesting process that takes a product that you would like to find some use of other than it being in the atmosphere, and then you can like cycle it through, pressurize it, it's a solvent, depressurize it, and it's not a solvent. Okay, and so then water is pretty high here in terms of its critical points. Water having strong intermolecular forces gives it a high set of supercritical points. Okay, so that wraps up our coverage of chapter 11. We'll circle back to some review of chapter 11 when we get to the exam review stuff after we talk about some chapter 12 topics. Chapter 12 has a lot of sections that we're only going to briefly discuss some little sections of. So our focus on chapter 12 is really just going to be on this first section of the chapter on classifying different types of solids and talking about some of their big differences in their patterns of either appearance or behavior. And so we're going to classify solids based on the type of bonding that's occurring within the solid. We're going to classify and talk about the different types of formulas and how we can look at a formula and tell what type of solid that substance is going to be. And then we're going to try to describe the difference between something that's crystalline and has an ordered appearance and appears more brilliant versus something that's more amorphous and has a random nature to its solid. And then the remaining sections here, like we might talk about some aspects of types of solids, but we're not going to get into any more details in those later sections than what's just in the very first section of the chapter. So just a couple slides here to introduce or to just review in some ways some different types of solids. Because we've talked about solids before in a few different varieties. Like we know there's some elements are solids, mostly are metallic solids, but there's also some non-metallic solids like carbon. We also know that things like ice can exist, and that's a molecular compound. So our first category of solids are molecular solids. And so these are cases where you have a molecular compound like water, like N2, like CO2. So anything that you think of as being a molecular compound that's in its solid form. And so it's holding the solid together, and something like water or CH4, N2, or CO2 are the same type of intermolecular forces that hold liquids together. So they're being held together by our basic intermolecular forces, so dispersion forces, dipole-dipole forces, H bonding forces, depending on the type of substance that's involved. Obviously, water would have all three. If we were comparing something like hydrogen bromide, that would just have dispersion forces and dipole-dipole forces, just like a liquid sample the substance would contain. And then it would also have the dipole-dipole force. Acetonitrile, we mentioned that compound in chapter 11. That's one of those ones that's polar but doesn't hydrogen bond, so it also has the dispersion force plus dipole-dipole forces. Iodine only has dispersion forces because it's a nonpolar compound. So I2 is nonpolar, so it's only held together by dispersion forces. Sucrose is like glucose. We showed the structure of glucose where it had all those OH bonds, and the hydrogen attached to oxygen allows for hydrogen bonding. Sucrose has two of those types of rings. It has a bunch of hydrogen bonding sites. And so this one here has all three. So it has the dispersion force, it has the dipole-dipole force, and it has the H bonding. And it has a high melting point. But notice that iodine's molecular weight's huge. I mean, iodine's 127 times 2 in terms of its molecular weight. So it gets a lot of dispersion forces. So it has just about as high of a melting point as sucrose does. So even though it only has dispersion forces, I2, it still can have a strong force of attraction due to the size of the molecule. And so even though acetonitrile and hydrogen bromide have that dipole-dipole force on top of their dispersion forces, they're relatively small. So HBr is so small, it's still a gas at room temperature. Acetonitrile is a liquid at room temperature. So you can get a sense that the stronger the intermolecular force is between a molecular substance, even if you can't exactly predict it. I don't know if we could have predicted the trend of these melting points here, but we could at least get a sense of the stronger overall the total intermolecular force is, then the higher that melting point's going to be. And so then the molecular solids, when you have a molecular solid, it's generally softer in structure. You're not going to like build a building out of molecular solids. You might think, would you ever want to build, maybe an igloo would work, but it's obviously going to melt, so probably not a great choice if the temperature were to warm up. So the nature of most molecular solids is that they're generally more like powdery, if they're at room temperature. So they're usually going to be more electrically insulating. They're not going to be something that you make conductive very easily. You're not going to make a wire out of something that's a molecular solid. It's not going to be able to pass charge from molecule to molecule. Electrically insulating probably won't be such a great, you probably won't want to use a molecular solid to wrap a wire because it's going to be too brittle to maintain an actual solid form around something like a wire. And you get lower melting points and boiling points generally for these substances compared to some of the other categories of solids that we're going to see. So we don't get a super strong force of attraction unless the molecule is really big or unless it has a lot of those hydrogen bonding sites on the molecule. So another category of solid that we've talked a fair bit about in the course already are ionic solids. And so ionic solids are, of course, where we have atoms that are ionized and then they're being held together through ionic bonding, through that lattice energy. And we've seen lattice energies are on the order of 800 to several thousand kJs per mole. And if you compare that to covalent bond strengths, the bond strengths that are holding atoms together in things like water, CH4, those bond strengths in covalent compounds are about 200 to 800 kJs per mole, maybe a little higher for double and triple bonds. But our covalent bonds holding atoms together generally weaker than ionic bonds. But then the bonds between water, those intermolecular forces of attraction, are much weaker than covalent bonding. So you can see that ionic bonds are held together by a much stronger force of attraction, and then you have a three-dimensional array of plus and minus interactions. So instead of having just water, two hydrogens attached to an O, and then that relatively weaker intermolecular force, here we have an entire structure connected by plus minuses. So you get a ton of these strong attractive forces through the electrostatic forces of attraction. But one of the natures of most ionic compounds, you can think of salt this way, that if you have a piece of salt, it's not too hard to break that into pieces. If you take you might not want to do it barehanded. If you have rock salt, you might want to take a hammer, but you can relatively easily shatter a piece of rock salt because you can sort of break this structure fairly easily and it just reforms and can exist if you break it in half and break it into smaller chunks. So you get a brittle nature to this type of solid. Electrically insulating, interestingly. If you think of an actual ionic solid, like NaCl solid, potassium sulfate, any type of solid powder is not going to be really easy to pass charge from one ion to the next because the ions have already passed their charges on to each other. Now, if you dissolve the ionic solid in water, then you could increase the conductivity of water. That was the electrolytic nature, if you recall. So if you put one of these compounds into water, you can make water more conductive. You can make water then more electrolytic than it was without those ions. So dissolved in water, you can pass charge to and from these ions, but not within the solid structure. So within a solid, you get a brittle nature, electrically insulating, but the melting point and boiling point nature of these substances is very, very high due to that strong attractive force, due to that strong lattice energy. So lithium fluoride, if you recall, for a plus-minus ion, has the strongest attractive force because we have the smallest +1 ion, we have the smallest -1 ion bonded together. So if you have a +1, -1, this is going to be as strong as we get. Notice that the melting point over 800 degrees C, boiling point over 1600 degrees C, really, really high, of course, in these melting points and boiling points. If you reduce the size, or if you increase the size of the ions, you put them further away, you reduce the attractive nature, you reduce the attractive force. If you remember, we're looking at the energy of electrostatic attraction is equal to kappa Q1, Q2 divided by D. So if you make those ions further away from each other, you weaken their force of attraction. So we can lower the force of attraction by just putting the ions further away. So NaCl ends up having a lower melting point. So if you weaken the lattice energy, if you recall from chapter 8, then you can also predict that you're going to weaken and lower the melting point and boiling point. So NaCl is a little bit lower than LAF just because its ions are a little bit bigger, hence a little bit less attracted together. And if you go to a 2+, 2-, we should increase the lattice energy. So remember, if you increase the magnitudes of charge, we increase the energy of electrostatic force of attraction. And so in that case, if you increase the charges, you make the ions more attracted together. It should take more energy to separate, more energy to melt and to boil, and that's exactly what happens. We have a much higher now melting point and boiling point. So NaCl is on the relatively low side of melting point and boiling points for +1, -1s, and then +2, -2 is even higher, and calcium fluoride with the +2, -1 is somewhere in between. So we're somewhere right in the middle when we have a +2, but with the other two ions being -1s. Now, something we don't talk too much about, but you might appreciate, is if you look at like potassium sulfate. What happens if you make sulfate ion, and then you have that relatively big now, because sulfate's a pretty big ion, molecular ion, and then two potassiums. What do you think the melting point of potassium sulfate would be compared to these ions here? Do you think it'll be a lot higher or a lot lower? Probably a lot lower. So let me just Google that real quick, because I'm sure it's probably like 200 or 300 degrees C. Oh, come on, where is it? Usually, well, maybe I was off. It was still pretty high. But if you make the ion bigger in molecular, generally you're going to weaken the melting point. So you can think of the size of the ion comes into play, that generally want ions to be smaller to have higher melting points or more highly charged. I should think my examples out before I make them up. Okay, so let's talk about another category of solids. So we've seen molecular solids or molecular compounds that are held together by intermolecular forces. Ionic solids are held together by strong electrostatic forces of attraction. What's holding together diamond? What's holding together graphite? So those molecules are being held together by networks of covalent bonds. And so we briefly talked about this before, where diamond is just where you have tetrahedral carbons. So you can imagine like something like methane being tetrahedral. Well, imagine you have methane, but in place of hydrogens, you put carbons. And then wherever there's carbons, you just continue having more carbons. And so you just have a three-dimensional array of carbon atoms. That's what diamond is. And so if you can imagine having a bond now, like the covalent bond is generally weaker than an ionic bond, but when you have a three-dimensional array of covalent bonds, you just have so many covalent bonds that they become very hard to break. And so what happens here is we get an extended network of atoms held together by these covalent bonds. You get a very hard structure. It's very hard to break these bonds because like if you break the bond in half, each of the atoms wanted to be together. Those electron pairs in the middle are acting kind of like a spring, and they're all kind of like blocked into place. So it's very hard to break those structures. The plus minus is, while there is a strong attractive force, it's relatively easy for it to overcome and survive without being right next to its partner. Carbon wants 4 bonds. If you break 2 of those bonds and try to break it in half, it's really trying hard to not allow that to happen because it needs those bonds so it can keep 4 bonds intact. So you get a hard structure, very hard to break a diamond. I still wouldn't recommend it, but it's going to be harder to shatter a diamond than it will a piece of salt. But it will eventually shatter if you hit it hard enough. So you can eventually get a diamond to shatter. So even though it's hard, you can put them in saw blades and cut with them. If you shatter them hard enough, they will eventually shatter into pieces. But they are variable in their properties. This is where a lot of metals that are in that kind of carbon to silicon to germanium, arsenic range, in the metalloid range of the periodic table, start to have conductive properties where you can turn their conductivity on and off. That would be what you think of as being a semiconductor. So an insulator wouldn't conduct at all. A conductor would conduct freely, pass electrons very easily through it with no resistance. A semiconductor requires some resistance or can be turned on and off depending on the electric force. And so you get semiconducting properties for things more like silicon than maybe you think of carbon, but for the metalloids, they're going to have these semiconducting properties, and their metal or their atoms are going to be held together through covalent networks. So if you think of silicon, silicon forms a very similar type structure to diamond, where it forms a three-dimensional array of tetrahedral silicon atoms. So silicon has a very high melting point and boiling point, over 1400 degrees C melting point. Germanium's also high. You can also make sort of pairs like gallium phosphide. If you take sort of, like if you go one over from silicon and the other direction over from silicon, so think aluminum phosphide or gallium phosphide or indium phosphide, you can make semiconductors out of those materials. Also have high melting points. The melting point of diamond's not shown on here, but I believe it's over 2400 degrees C. So diamond, very high melting point and boiling point. So you get super high melting points and boiling points due to the nature of these solids having all those covalent forces of attraction holding their atoms together. SiO2, in glass, has a really high melting point as well. And so this is present in glass or in quartz. So high melting point for SiO2, also held together through a three-dimensional array of carbon atoms. Now I mentioned this for SiO2 to kind of separate it from CO2. CO2, for whatever reason, isn't able to adopt the covalent network solid nature of its solid, so it just has discrete intermolecular forces holding CO2s together. SiO2 does something like this, where all the atoms link together in the structure, forming a much stronger structure. So you can think of how glass has some strength, but also can be brittle. So if you're thinking strong but brittle, not making much sense, think about how strong a piece of glass can be, but also at the same time, if you hit it the right way, it can break. So it's hard solids, but brittle. Now I think this is the last category of solid, but that we'll talk about. But polymers are one that we'll just briefly touch upon here. They're long chains of atoms held together by covalent bonds, and then the chains can be cross-linked together or attracted together through electrostatic forces of attraction. And so you can think of things just like repeating groups of carbon and hydrogen atoms, and you can have other atoms involved as well, but the properties here are going to vary. You can imagine polymers that are like hard plastics, you can imagine polymers that are soft plastics, you can imagine polymers that are more like styrofoam, you can imagine all different types of polymers that have all different types of characteristics. And generally though, you're going to have electrical insulating polymers, though you could have conducting polymers, but you tend to think of plastics as wrapping wires because they are so insulating, and they're also bendable. They have all the properties that you would want a substance to have. They last a while. They don't tend to degrade, at least all that quickly. And so you can have things like polyethylene. What this is if you just have simply the CH2 group. So if you imagine the repeating group here, how you can characterize a polymer is, well, what is the group of atoms that's repeating? So if you imagine the simple repeating pattern is just the carbon, hydrogen, the CH2 group. If that's your repeating pattern, that's polyethylene. That's your saran wrap. So this is your very simple plastic. If you replace and just add a chlorine to one of these spots, if you have one of those hydrogens replaced with a chlorine, that becomes polyvinyl chloride, PVC. This is that harder plastic you think of being in like the dashboard of your car. If you then think of polystyrene, where we replace that hydrogen instead of with a chlorine, if we replace this with that sort of benzene ring, so if you have this replaced with that benzene ring, which you don't have to know the structure here, we're just replacing it with that C6H5 ring, then that becomes styrofoam. And so that's polystyrene. And so that then has that styrofoam appearance. And then if you have a different amount of carbons, if you have C5H8 as your repeating pattern, then that's the basic structure of rubber. And then if you cross-strand connect those strands together with like sulfur atoms, that's called vulcanization. If you cross-strand connect the strands of rubber together, so your long chains of polymers are held together very strongly through covalent bonding, then that's what you think of as being in your car tires. So you can have all different types of polymers. These are just a few types. But the key classification for polymers, you have some sort of set of atoms that repeats. And this is going to repeat up to like thousands, if not millions of times in the structure. So you're going to end with a very long molecule. And as you have a really long molecule or compound, it's going to have that strong intermolecular force of attraction with its neighboring atoms it's going to intertwine with. And so that's what plastics benefit from, is not just all of those covalent bonds like left to right in the structure, but then the cross-linking of the structures through that really strong dispersion force because these particles are so big. So you get the long chains of atoms connected together, and then those chains are held together by that weaker but collectively strong intermolecular force, usually dispersion forces. Okay, and so the melting point and boiling point trends of polymers vary. You can think of these substances generally melting pretty low, like they will burn and break down. So they generally don't hold up to heat so well, but you can play around with the chain that you're repeating and come up with all different types of properties for polymers. Oh, I'm sorry, there's one class category, solids. But this category we've been talking about for a long time, and that's the 2/3 of the elements in the periodic table that are metals at room temperature, and all but one of them are a solid. Of course, all but mercury and the metals are a solid at room temperature. And so it's holding metals together. We call that metallic bonding. We've talked about this a little bit. So the extended networks of atoms held together through metallic bonding, or what we call our metallic solids. So examples can include magnesium solid. which has a 650 degrees C melting point. Silver is over 900 degrees C. Titanium, almost 1700 degrees C. Tungsten, we used to use it a lot in light bulbs. We're trying not to use it so much anymore. But if you think of the old style light bulbs that would get really hot, that were then replaced with the LED light bulbs, we used to have a tungsten filament in those light bulbs in the old-fashioned 60-watt, 100-watt light bulbs. But you'd have a little piece of tungsten that would be absorbing electrical energy, creating high-energy tungsten, which then coalesces back towards its ground state, and eventually has a melting point of over 3,000 degrees C. And so metals can have really strong attractive forces because you have all these metal atoms connected through a relatively strong metallic bond. And the interesting thing that we've talked about a little bit before is how lithium has a higher melting point than cesium does. So if you go from top to bottom of most of your metals, if you have the more metallic character that a given element has, then the more you're going to get this trend that's followed, that where you have a bigger metal has actually a lower melting point. And then as we actually go from left to right across the periodic table, the metals are becoming more non-metallic in their appearance. This is why if you go zinc, cadmium, mercury, that mercury is the one that has that lowest melting point. It's because it's kind of picking up that, well, that actually shows you the metallic trend, right? Because that's showing you the decrease in the melting point as you go from left to right. And then as you keep going, eventually your metals are going to start to blend with those non-metallic properties, and you're going to go across the metalloids and back into non-metallic elements. And so lithium's melting point is around 200 degrees C, and then cesium's melting point is only around 30 degrees C. So just because it's a metal doesn't make its melting point super high, but a lot of metals can have really high melting points though. And so, so melting point trends, generally decreasing melting point as you go from top to bottom. Not necessarily a trend I would expect that you're ever going to get tested on, but I think that's just an interesting property or an interesting thought that there must be charge involved. Because the thought of charge being exchanged, being smaller is better. It's easier to exchange charge, or the exchange of charge is more attractive. It's more important for holding those molecules together when they're smaller. If we're taking the same charge in cesium and passing it through a bigger atom, we get a weaker force of attraction. So it's just like that lattice energy, where if we have bigger ions involved, lower lattice energy, bigger metal atoms involved, lower melting points. And so metals have relatively strong bonding. So even if you have a relatively low melting point metal, it's still generally pretty strong in its appearance and its properties. And so you can also, two words that often get attributed to metals that aren't attributed to any of the other categories of solids is that they're malleable and ductile. And this just means, malleable means you can pound them into sheets, and then ductile means you can stretch them into wires. So you can make wires out of most metals, you can pound most metals into a sheet, make sheet metal out of them. They're generally the best conductors of electricity of all the categories of substances, with maybe the exception of ionic solids dissolved in water. So you can get good electrolytic behavior for ionic solids but dissolved in water, but you also get this for our metal solids. So our metallic solids, good conductors of electricity, also good conductors of heat. You can think of an equivalent weight iron skillet compared to a water pot on the stove. The iron skillet's going to heat up a lot faster because it's just that much more good at conducting heat. That's another way of saying it has a lower specific heat. If you go back to chapter 5, the specific heat of iron is really low, specific heat of water is really high. It takes a lot of heat to heat up water. We get generally high melting points and boiling points for metals. Even though some of them can have relatively low melting points and boiling points as a category, we have relatively high melting points and boiling points. So one way we can think of metallic bonding is that most of our metals, if you think of iron, if we're counting valence electrons from chapter 6, how many valence electrons do you think iron has? So we'd have a 4s2, 3d6 configuration. So I'd say here we have 8 valence electrons. And so if you think of bonding this way, if you just go covalent and ionic, covalent bonding shared electron pairs. So do the atoms share their electrons, or does one atom steal an electron, the other one goes plus, the other one goes minus, and you get that force of attraction? Or what if the alternate for metallic bonding is, what if all those electrons are everywhere? So what if there's so many electrons that we can't really figure out, is this electrons, this atoms, is this, like, where does that one electron belong to? Does it belong to the one or to the other, or is it just kind of flowing almost like a solvent? One of the best models of electrons in a metal is that it's almost just like a fluid, that the electrons are almost like acting like a fluid, and if you take part of the fluid away, the electrons just flow very quickly like you would imagine water would flow. If you take a little bit of water out of a pipe, all the rest of the water is going to flow towards it. Take an electron away, all the electrons flow towards it. And if you add an electron, all the electrons are repelled, so they move away. So you can picture the number of valence electrons being relatively high for metals, and that they're all just flowing freely through the metal, giving it that conductive set of properties, giving its thermal conductivity. This is how you can sort of imagine the electrons just flow as we push the metal atoms around. So if we try to pound a sheet of metal, the electrons just flow with the metal as we move those nuclei around. If we try to stretch, the electrons just stick with they just find a way to flow as you're stretching the nuclei. And so this is called the sea of electron model to help you understand, or to help understand how metals have some of their properties. And it really gives us, I think, a better picture of almost the three key types of bonding being shared electron pairs, that's covalent bonding. We then have donating, accepting and donating is ionic bonding, and then just like the complete sharing and like the surrounding of the nuclei with the electrons as the metallic model of bonding. This slide here is showing us as you go from, like if you picture tungsten, we said had a high melting point, that it's kind of interesting that some metals will be relatively high as you go from top to bottom. We don't always follow the trend of decreasing melting points. So tungsten and rhenium are going to have the highest melting points of all the metals in the periodic table, but they're going to peak out in the middle of the transition metal row and then start to drop off. And so as you go from left to right across the transition metals, you get this like really interesting set of properties that the third row metals here are melting the highest in the middle, but then the lowest on the fringes. Really is kind of hard to comprehend why that might be the case, but it just turns out to be the case. And it's not something that you need to memorize, but it's just, I think, worth pointing out that as you go from left to right, that all of our transition metals are peaking out in their melting points around the D4, the D5, the D6 configurations, and then we're falling off from there. This helps us try to understand how it is that some metals like iron have a really high melting point, but then some atoms like zinc, cadmium, mercury relatively low on their melting point sides. And so, so that's just an interesting trend of melting points for transition metals. And then on the topic of crystalline versus amorphous solids, like I think we all have seen crystals before. I think we can understand that certain substances will appear more brilliant than others in their appearance. And what's going on, the explanation at a molecular level would be that there must be some ordering. So if we have like iron pyrite, there just must be some way that those atoms are ordering, that the atoms are just ordered in exactly the same pattern, so that when light hits one piece of the solid, it reflects off in the same way on every piece of the solid. If you have an amorphous solid, if you have all the atoms just kind of randomly, when light comes in, it might bounce off this way, it might bounce off this way. Light's going to bounce off in random directions when we have an amorphous solid. So an amorphous solid is where you have a bunch of atoms that are just randomly distributed in the solid without any particular pattern of their arrangement. So things that are crystalline, you can imagine they must have some crystalline structure. They must have some like repeating pattern that repeats itself, so that repeating pattern is reflecting light in exactly the same way. So crystalline solids, the atoms adopt an ordered repeating pattern. This gives the crystal sort of a more brilliant appearance as a result, and the amorphous solid lack that kind of order of their atoms, and so they don't reflect light in any special kind of way. They appear to be more dull in their appearance. And so one interesting example of this in nature would be quartz. In nature is crystalline. And so this is how we mine SiO2. So this is quartz. In quartz, it's not super brilliant. You can see there's a lot of imperfections in the crystal. So you can see it doesn't appear to be perfect in nature. Let's actually take a step back and think of diamonds for a minute. We all think of how brilliant the appearance of a diamond is, how bright a nice shiny diamond can be. That's because light's reflecting off of the carbon atoms in that nature in exactly the same way. I think I had mentioned the 4 C's of diamonds in this class before. I think we were talking about this at some point on the color, clarity. Do you remember these, Aaron? I don't know, but the color, the cut, the clarity, and something else. But the color of a diamond, if you've ever seen or heard, if anybody's ever been in the market to buy a diamond, The color of the diamond, like a diamond can get a yellowish color from impurities. So if one of those carbon atoms happens to be a phosphorus atom or a sulfur atom or some other type of atom, the diamond is going to lose that reflective nature of light. If you have enough of those imperfections, then the diamond can actually appear to be a different color. And so, or maybe under a microscope, you can see this different color. And so you're getting the imperfections in that crystal structure will give you some of those defects in a diamond, because no diamond is 100% carbon in every single spot of that lattice. Some of the spots might have a carbon missing. But if you have all the carbons exactly there, light reflects very brilliantly off a diamond. But you can see here we have some imperfections in this quartz. So quartz is SiO2 with a more ordered pattern of the ring. So if you notice here, there's a very specific pattern that quartz will have, or at least most of the time. Now, how you make glass out of quartz is you melt the quartz down, so you heat it up to 1600 plus degrees C, so it turns into a liquid, and then you let it fall into a sheet, and then you let it cool. And then how fast you let it cool, or how you anneal it afterwards, if you let it cool and then heat it up a little more and then let it cool some more, then you can get glass that's actually pretty relatively strong, though still brittle. So glass is where you lose that repeating pattern. So notice here that we have different ring sizes. We have broken rings, we have closed rings, we have random now patterns of SiO2 instead of a very standard pattern of SiO2. So here we have a crystal pattern, we have a crystalline pattern, and here we have an amorphous pattern. So we're more amorphous with SiO2 glass than we were with quartz. So no repeating pattern loses that brilliance of appearance, so light isn't reflecting off of the glass anymore. In fact, it can go straight through. And so if we maintain a lot of random groups, we might have groups that would then be reflecting light. That's why light's not going straight through the quartz. So in other words, being more ordered in your pattern allows a structure to be more brilliant in its appearance. NaCl, or ionic solids, kind of by nature have to have some sort of pattern to them, because you have all these plus minuses. They're going to have to fall into some sort of a pattern. We see here NaCl has a pattern that really would look like this, where all the atoms are kind of just, wherever there's a chlorine atom, there's a sodium right behind it, and then there's a chlorine right next to it. And so you can imagine light should reflect off this crystal in a particular pattern. So table salt, though it's not a brilliant color, but you can think of some ionic solids, like if you think of copper sulfate or copper nitrate, nice blue color. If you make that into a relatively big crystal, it will be a very brilliant appearing crystalline solid due to the nature of the plus-minus interactions in that solid. So we get crystalline solids for ionic solids. We get crystalline solids, actually, we get that regular pattern for metals. You can think of like the brilliant appearance of a metal, and that's going to be due to the metal adopting some sort of a regular pattern. And that is like part of chapter 12 that we're going to skip, is talking about, well, what are those patterns? How can we describe those patterns? How can we take those patterns and understand densities of metals? Trust me, it's not worth the effort to go through this. There's some very tricky calculations if you were to skim through chapter 12 that we're not going to talk about, which is good because those calculations are hard. But the idea would be that different metals can fit into different types of patterns, and different metals, different ionic solids have this crystalline nature about them. And so this is just showing a few different types of crystal structures. Like cesium chloride adopts a different type of structure. You don't have to know that it does, but it just happens to have a different crystal type structure than NaCl does. So instead of having the cesium right behind a chlorine, it's actually more like in the middle of a box with like 4 chlorines stacked above and below it, and that's the repeating pattern. But it does form a crystal nature. Zinc sulfide has a particular nature. Calcium fluoride has a particular pattern. So our ionic solids have some sort of a repeating pattern that allows them to be crystalline in their nature. We see this with diamond. We see this with graphite. Graphite, though, we should mention that graphite is kind of like diamond, but it's just a 2-dimensional sheet of carbon atoms. And then those sheets are connected through intermolecular forces. So graphite's very interesting in that it's kind of like that polymer, right? It has like a 2-dimensional array of atoms, and then the sheets are connected through that dispersion force of attraction. And so that's why our graphite, when we use a pencil, these sheets of graphite are just more easily able to slide off each other. So when you use a graphite pencil, the sheets of carbon are just separating off of each other. Interestingly, people for a long time wanted to image a single sheet of carbon atoms. And you know how they were able to do it? was by taking a piece of Scotch tape onto like the end of a sheet of graphite and peeling off just one of those strips of graphite and then getting an image of just one single sheet of carbon atoms. Very interesting experiment, but also interesting, they just literally use a piece of Scotch tape to do it. And they could do that because that's a relatively weak set of forces. The fact that these sheets will slide off each other shows you that there's not a whole lot of force holding the two sheets of graphite together, but there's a strong force holding the entire row of carbon atoms together because you have all those covalent bonds. So we get crystalline nature for our covalent networks, we get crystalline for our metals. So you can think of how different types of solids can fit into these crystalline type structures, but then our molecular solids are just amorphous. So if you think of ice, if you think of dry ice, those are more amorphous, random nature, no specific pattern of the atoms in those structures. And so that kind of completes our coverage of chapter 12. So the main things to know from chapter 12 are those 5 classifications of solids, what makes them different from each other, and then some molecular picture that we're talking about here of what makes those different types of solids different from each other. And then that's about it for chapter 12. Okay, so this information here is posted with the final exam set of review problems. So this is on Carmen in the final exam review set of problems. So yeah, final exam is next Thursday at 10 a.m. I don't know if they've announced the room yet. I suspect it will be here, but I'm not entirely sure that's the case. But usually it's in the lecture room. It's not in your recitation room, so recitations have met for the last time. And so the last meeting we have of the semester as a class is next Monday here at the usual time. Monday's the last day of regular class. So we'll have class Friday and Monday still to go. The final exam will be about 50 questions. You'll have double the time of a midterm. So the exam you'll get an hour and 40 minutes, so 100 minutes for the exam. It'll be cumulative through chapters 1 through 12. We will continue to skip the topics that we've skipped along the way. I don't know if it would probably take me too long to talk about all the things that we've skipped, but if you look back at some of the messages from midterm 1, 2, 3, 4, etc., you might see some of those sections that we had skipped from those earlier chapters. If you look at some of the daily quizzes, some quizzes are marked with questions that we haven't covered that you don't have to worry about. You might take note if you're looking at some of the daily quizzes on those questions. I think the ones to me that stand out are the CO2 water problems. We were trying to get a formula off of how much CO2 or water are present. Don't worry about those problems. That's in the middle of chapter 3. We skipped that problem. We skipped activity and using activity series in chapter 4 to predict reaction trends. And we skipped the second half of chapter 7. We skipped most of chapter 12 as we mentioned here today. Okay, so there's, I have some practice final packets in the daily quiz area. I think the department posts, I think there's 2. Has anybody looked? I think there's 2 practice finals that the department posts. I think one of them is the PDF or a PDF version that I have posted. To be honest, they stole my final exam, so they stole it from me to post it for the department. But so there are some practice final materials. There's also, I have posted some chemistry Olympiad exams. These are things that you may have taken or seen or heard about if you took AP in high school. It's like a competitive chemistry exam. But they post all these practice exams and all the actual exams they give in throughout time. And it's an interesting set of review problems because it has essentially a very similar set of problems that we cover. But you might see some of those posted in the daily quiz area. And then just try to, like, I would highly, highly recommend that you start your studying for a given chapter, or if this is minimally what you do, just read the chapter summaries of each chapter. Not necessarily all in a row, but maybe read chapter 1 summary and then try to review things from chapter 1 that in your mind you don't remember as clearly as you want to remember. As you read through that chapter summary, maybe something will pop up as something you forget about. And then, so maybe spend 30 to 45 minutes per chapter. Move on to another chapter, do kind of the same process. But reading the chapter summary should give you a really good review of what the chapter was about, and then a good kind of like push to go review things in that summary that don't make any sense or that you've forgotten about. We'll do some review problems here. I can get to a couple here today before we depart. The first question or 2 come right from chapter 11, so I think looking at a question or 2 today would make sense. And then I do have some extra office hours, so starting Friday, right after class at 12:30, that's an extra office hour, then the regular one from 2 to 3. Same thing Monday, the same office hours, then Tuesday and Wednesday next week, 10 to 11:30, and then 2 to 3 both days. So stop by. If you haven't come into office hours yet, if you have any questions from any exam, any quiz, any topic that you just don't understand, you can just say, hey, can you show me how to do this problem, and I'll show you how to do it. So if you ever get stuck on anything, just drop by. Happy to help you through whatever problems you have. And so let's look maybe at 2 or 3 problems before we wrap up for here today. So this one here on a phase diagram. So here we see, and we can label this a little bit. We know this should be the solid phase. We might notice this is pressure and temperature. I don't think we tend to confuse you too much by reversing the temperature and pressure on the axes, but you want to probably take note that pressure's on the y-axis, temperature's on the x-axis, and then we have our liquid phase here, our gas phase here. Above here would be our supercritical fluid. And so, so one of the questions it says, which of the following is false? I hate those kinds of questions because I always end up trying to find the true statement. But the solid has a higher density than the liquid. So here's the solid. So the best way to think about density, I think, is if you add to the pressure, if you increase the pressure, so you're putting pressure onto the solid, you're pushing the solid closer together, that's increasing the density. So by pressing the solid molecules closer together, that's increasing the density. When we increase the density, all of a sudden the substance becomes a liquid. And so when that substance becomes a liquid, then the liquid has the greater density. And so the solid does not have the higher density. The liquid has the higher density because I pressurized the solid and it became a liquid. Okay. And so that should be the false statement. And let's go through the other statements and try to see that they're true. And so sublimation and deposition are the only phase changes possible at temperatures and pressures below point B. That's point B. And so when we're below point B, the only phase change we can go is solid to gas or gas to solid. So below the triple point, the only phase changes that are going to occur are solid to gas in either direction. So we change temperature, we can go from solid to gas. We change pressure, we can go from solid to gas. I suppose we can go solid to liquid if we're over here too. But yeah, so I'm thinking phase change here from if we're changing the temperature. So changing the temperature is the only phase change. So let's not worry about changing pressure on that question on point B. We're just thinking about changing the temperature. Point C, no phase change occurs when the liquid phase is compressed at constant temperature. So if you imagine taking the liquid phase here, and then you compress it, is going upwards in pressure. So compressing is adding pressure. We compress the liquid phase. If you notice, there's no point at which we become any other phase other than staying liquid. And so that would be a true statement. And so when we heat this thing at 1 atm, so 1 atm is marked here, the substance will first melt, solid to liquid, and then go from liquid to gas. That's entirely true. This substance at 1 atm will go through a normal melting process to a liquid, then a normal boiling process to a gas. And then it's possible this is the phase diagram of water. I would say it's possible. That's still not the right answer. Like, it's a true statement, which makes it not the right answer. We're looking for the false statement. So this statement is true, that this could be water, because water has the normal melting point and boiling point as kind of indicated. It has a liquid that's more dense than the solid. So it has all the properties that this phase diagram is showing, other than maybe this one's just really showing a slope on that solid liquid curve that's really pronounced. Okay, so that's that one there. A should be the right answer, that the solid is not of higher density than liquid, according to that phase diagram. And let's wrap up with this slide here. So the vapor pressure of CH3F is 3.3 megapascal. Let's not worry about what that means per se, but you might remember mega is 10 to the 6, so that's 10 to the 6 Pascal. And then the vapor pressure of CH3Cl is 0.5 of that same unit, so that's lower. So the vapor pressure of CH3F is higher, CH3Cl is lower. And so now what explains the trend? And so now vapor pressure, if we think about vapor pressure, what makes vapor pressure higher is weaker intermolecular forces. This is inversely proportional to intermolecular forces. So if we weaken the intermolecular force, you make it easier for a particle to escape into the gas phase, which gives that substance a greater vapor pressure. So vapor pressure was the one property we talked about in chapter 11 that had an inverse relationship to strengths of intermolecular forces. So we weaken the intermolecular force, we increase the vapor pressure. So this must mean that CH3F has the weaker intermolecular force, because that's what gives it the overall greater vapor pressure compared to CH3F. So now the difference between the two compounds is CH3F or Cl, they're both polar because they both have an electronegative F versus chlorine. Fluorine's more electronegative, so you might think CH3F's more polar, and it probably is, but it's smaller. So CH3Cl is the one that has stronger intermolecular forces because it is bigger, has a greater dispersion force. So what CH3Cl is benefiting by is just by being heavier than fluorine. So the extra size of the chlorine is giving it that greater dispersion force of attraction. And so this has really nothing to do with the electronegativity difference of F and Cl. It's because we have a greater dispersion force. Sometimes it's called a London dispersion force. We get a greater dispersion force in CH3Cl. It's not due to the stronger dipole-dipole force. If that were the case, CH3F would have had a lower vapor pressure, not a higher vapor pressure. And it's not due at all. Vapor pressure, intermolecular forces have nothing to do with the bonds between the atoms and the molecules. It's all to do with the strength of force between the molecules. And it's not about hydrogen bonding. The molecule can't hydrogen bond. You have to have H directly attached to F. And so the answer has to be that one that I circled. We'll move on to the next question next time. So that's all for today. And I'll see you guys on Friday.